Hello, hello, hello. I hope I am audible. Let me just check it once, then we are starting with today's lecture. Hope I am audible. Just check it once, then we are starting. Okay, is audible. So, let's start with today's class. Today we are going to start from a new chapter. Sorry, start with a new chapter, that is D and F block. We have completed solutions. I know that a few videos are yet to be there on YouTube. Sure, it's as soon as possible on YouTube. Okay, like the last part, the colligative property part is left, so I will try to ensure that videos come. Okay, but the notes of that part have already been shared in the community, in the WhatsApp community. The notes have already been shared, so you guys can go there and check it. Okay, so today we are going to start with a new chapter, and inorganic chemistry's first chapter in your revised syllabus, that is D and F block. D and F block will be, this chapter is basically an easy chapter, and how we are going to deal with it, let us first see it once. D and F block, basically this chapter is related two parts. Okay, one part is the reaction part, which we will be dealing in one separate lecture, and the theory part, right? Theory part which will have both D and F block. So D and F block theory, that we will be dealing with, this part is lecture number 1, which is today, and reaction part will be taking part in lecture number 2, which will be the next lecture. But we will only deal with the reaction. It is going to be a very short lecture, because you can understand the reactions are only of dichromate and manganate, right? So that will be taken in the next class. So today's class will be based on the theoretical parts of D and F block. Okay, so let us start with the chapter, with the, I hope that you will enjoy this chapter. Okay, I know inorganic people don't enjoy, but that's a different thing. But if you read, you will find that this chapter is a very easy chapter, and you can score. Actually, you can score from inorganic. This is the main thing that I have to say. Because after DNA block, we will start with coordination, and in coordination, you have to read properly, because there questions will be coming in a twisted format, but here there is no twisting of question. Direct question will be asked. Give reason, complete the reaction. So if you know the reaction, there is no problem. Okay, chalo, let us begin. First we'll be learning about transition elements. So transition elements will be divided into four separate series, because transition elements in the periodic table are divided into four periods. So according to that, we have divided into 3D series, 4D series, 5D series, and 6D series. Okay, if I can show the periodic table here, think I have it. Periodic. All right. So you can see the periodic table. So here if you see the periodic table, then you can see that scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. This is the first transition series. This is going to be the second: yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, cadmium. This is going to be the second transition series. Lanthanides will be starting from here, and it is continuing over here. Okay, these are all lanthanides. So this is lanthanum, this is hafnium, tantalum, tungsten, rhenium, osmium, indium, platinum, gold, mercury. This is the third transition series. Actinides are starting from here. Actinium is here. Okay, rutherfordium, dubnium, spurzgium, borium, hassium, metallium, drumstadium, rhenium, and these are the yet to be discovered. Okay, 112 is the last element of the transition series. So there are total 4 transition series, right? That is 3D series, 4D series, 5D series, and 6D series. Alright, so now let us have a look at it. 3D series is starting from scandium ending at zinc. So 21 to 30. In 3D series, the 3D orbitals will be filled. Alright. 4d series starting from yttrium ending at cadmium, filling up the 4d orbitals. 5d series is starting from lanthanum. Lanthanum is not a part of lanthanide series, but the lanthanides follow lanthanum. That is why the name is lanthanides. Okay, so lanthanum 57 and again from hafnium to mercury. Okay, so 57, 72 to 80. Clear? Next, 6d series filling up the 6d orbitals, and it is starting from actinium 89 and again from atomic number 104 to 112. Alright, clear? Easy thing. This is a basic thing. Alright, next we have to study about the electronic configuration and the general properties of transition element as in a syllabus. So starting from electronic configuration, we have general electronic configuration of transition elements is n minus 1d 1 to 10 ns 1 to 2. If it is asked in the question paper, write down the electronic configuration of transition elements, and you have to write this general electronic configuration. Like basically the question will be asking about comparison between lanthanoids and actinoids. The basic question that is asked is comparison between lanthanum and actinides. So let's go to F block and we deal with that. But if the transition elements electronic configuration is asked, then you can directly write it like this. Clear with this? Okay. Next, chromium and copper, they have exceptional configuration. This question already in chemical bonding of class 11, it has been discussed almost 5 to 6 times. Again here we are coming back to that question, which actually you all know the answer. Chromium and copper have exceptional electronic configuration due to symmetry, due to higher exchange energy, due to stability. So what is the actual reason? Reason is stability of partially filled or half filled and full filled orbitals. Partially filled and full filled orbitals, right? Why they are stable? They are stable due to higher exchange energy. Due to higher exchange energy, which has been discussed in class 11 chemical bonding. Okay. Achha. Let us see once. Chromium's electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 is wrong, 4s1, 3d5. Okay, I think it is done. 2 plus 2, 4, 10, 12, 18, 19, 24. So this is the configuration where a change is in the last part here, because half filled orbitals are more stable than full, the not half filled or full filled. So that is why one electron jumps from the 4s to the d orbital. Done. Similarly, if I go for the copper, if I go for 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. Okay, so here you can see that d orbitals are getting fulfilled. D orbitals are getting completely fulfilled. So they again are more stable. So this is why copper and chromium, they have exceptional electronic configuration. Next, transition elements. So we are saying transition elements. First of all, why it is called transition elements? It is called transition elements because this group of compounds are located in between the metals and the non-metals. Group 13 onwards, the non-metals begin, right? Metalloids are there in between. That's a different issue. But from group 13 onwards, the metalloids, non-metals are beginning, right? And group 1 and group 2, they are the metals. So these transition elements are lying in between the metals and the non-metals. So they are called transition elements. Transition from the metals to the non-metals. Alright. So now what will be the category or what will be the criteria that one particular element will be called as a transition elements? You might have the question that why is the p block elements not transition elements? Why are the s block elements not transition elements? So transition elements will be those elements only which will have incompletely filled d orbitals either in the ground state or in the ionic state but not any random ionic state in the ionic state which exists, like most significant oxidation state. Okay, so most important word is incompletely filled d orbitals. I am highlighting the word incompletely because that is the keyword. Though definition will not be asked in the exam, but I am just saying elements which will have incompletely filled d orbitals, either ground state or in ionic state. Clear? Understood? Like copper does not have incompletely filled d orbitals in ground state, but in Cu2 plus it does have, right? Because one will go from S and one will go from that. So 3D9 it will happen. Clear? So that is why copper is a transition element, but zinc is not a transition element, because you go for zinc 2 plus or zinc, does not matter. Both of them do not have any unpaired electrons. Okay, let us say zinc is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. And if I go for Zn2 plus, then it is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. So you can see in both the cases there is no unpaired electrons in the d orbital. So therefore they will not be considered as a transition element. But we will study it under the d block elements because of their similarity in properties with the d block elements. We will study it under transition, but they are not considered to be the transition elements because of absence of any unpaired electrons in the ionic or ground state. Clear? Zinc, cadmium and mercury, these three are the exceptions. Okay, they are in the same group, so obviously they are going to be considered as a non-transition element. All right, clear with this? Okay, next, general properties of transition elements. From now we are beginning with the important part of the chapter where give reasons will come in the exam. Here direct give reasons will come in the exam. Okay, they will be putting in one line and you have to answer why it is so. Clear? So first let us see atomic size. First we will see atomic size. Okay, if you have read class 11 periodic table, then in periodic table you have read that atomic size decreases as we move from left to right of a period, and down the group the size increases due to increase in the number of shells, right? And along the period it decreases due to increase in the nuclear charge. Correct? This is done in periodic table. Now here in D block, let us see what is the question saying. In general, the atomic radii of transition elements belonging to a particular series decrease with increase in atomic number. The decrease becomes small after midway. So first line is very obvious because that is what we have read in periodic table, that as we move from left to right, the atomic size will decrease due to increase in the nuclear charge. First line is not a problem, but the second line is a problem. What is said? The decrease becomes small after midway. Why is it decreasing, or why is the decrease becoming smaller? That means the difference is becoming smaller. What is the reason for that? The reason for that is the shielding effect, which you have learned in class 11. What was shielding effect? Shielding effect was basically the outer electrons are getting protected from the nuclear pool, right? Due to the inner electrons, not inner electrons, but due to the penultimate electrons, right? So in case of d block elements, there are d orbitals, there are d electrons present. তার বাইরে গিয়ে 4s electrons আছে, and 4s electrons are the outermost electrons. তাহলে d block or the d orbitals or the d electrons, they are shielding the 4s electrons from the nuclear pool. So what will happen? Understood? Clear? So the size will decrease. Size will decrease, and that is written also. The size will decrease, but the decrease will become lesser due to the shielding effect. The expansion of the electron cloud will not happen. Clear? Sorry, the contraction of the electron cloud will not happen. Clear? If atomic size, if the nuclear charge increases, the electron cloud will be pulled towards the nucleus. No, তাহলে বাইরের ইলেকট্রন ক্লাউডটাকে নিউক্লিয়াস ভিতরে টানছে না, তাহলে সাইজ অতটা কমছে না। দ্যাট ইজ দ্য মেন পয়েন্ট। ডিড ইউ আন্ডারস্ট্যান্ড? তাহলে as we are moving from left to right across the d series, any particular d series, then what we will see is number of d electron increase করছে, correct? For this you have to remember the configuration. মনে করো স্ক্যান্ডিয়ামে 3d1, তাই তো, ভ্যানাডিয়ামে 3d2, টাইটেনিয়ামে 3d3, ক্রোমিয়ামে 3d5, বাট 4s1, তাই তো, ম্যাঙ্গানিজেও 3d5। সো ক্রোমিয়াম আর ম্যাঙ্গানিজ দুটোর ক্ষেত্রে 3d5 হয়ে গেছে, তাহলে চেঞ্জটা কোথায় আসবে? চেঞ্জটা আসবে 4s এ, 4s1 আর 4s2। বোঝা গেছে বোঝা যায়নি? তাহলে এদের মধ্যে ডিফারেন্সটা ইট উইল বিকাম লেসার, the difference between chromium and manganese will become lesser as compared to before. Clear? Difference will become lesser due to this type of things. Clear? So what we will write for this is, for the first part do I need to mention? For the first part is increase in nuclear charge. So atomic radii of transition means decrease in increase in So if I am mentioning this one, decrease increase in atomic number, this is due to increase in nuclear pool, right? Increase in nuclear charge, right? But this difference which becomes small after midway, this is because number of d electron increases. Okay, you have to write that number of d electron increases as we move from left to right of the period. ঠিক আছে? আচ্ছা, d electron increases, therefore shielding increases. Clear? So the main point that you have to write in your answer is number of d electron increases and either the shielding effect increases. And what will happen the shielding effect increases? Then the nuclear pool is counterbalanced by the shielding. The nuclear pool or the increased nuclear pool is counterbalanced by the shielding. Is counterbalanced by shielding effect. Counterbalanced by shielding. So did you understand what you have to write in the answer to get marks? Don't write here and there beating around the bush, writing something which is not to the point, invalid, will not fetch you marks. You have to write whatever is completely needed. Okay, clear? Did you understand? I am repeating again. In general, atomic radii decreases as we move from left to right of a series. That is due to increase in nuclear charge, and that is a very obvious answer. But the second line is your problem. The decrease becomes small after midway. So if the question comes like that why does the decrease in atomic size become small after midway, then your answer will not be due to increase in nuclear charge, because it should have been decreased normally. Then why the decrease becomes small, or the reference it will become small? The answer is due to number of d electron increase, the shielding increases. So the shielding counterbalances the nuclear pool. That is why the difference between the size decreases. Clear? Right? Achha, difference between whom? Difference between one element and its preceding element. Not like that element, the first element of the series. No, therefore there will be a lot of difference between that. But between two elements in the middle, their difference will be lesser. Clear? Next. Near the end, this is the second part of under atomic size only. Near the end of, and this is from your book, this is from your book, you can see. Near the end of each series, there is a slight increase in the atomic radii. This is a very important question. As you are going towards the end of the series, whether it is the group zinc, cadmium, mercury, their size is comparatively more than the preceding element. What should have happened is the size should have decreased. Size should have decreased. So zinc should have got the least size, but this is not the case. Zinc, cadmium, mercury all are having greater size or bigger size than the preceding element. Why? The question is why? Question is why? Same reason as before, but you have to write in a different way. See, as I am saying that we are moving from left to right, the number of d electrons increases. So if the number of d electron increases, then you tell me at the end of a series, how many d electrons will be there? 10 d electrons, right? I accept that shielding will happen, but along with shielding, now there will be interorbital repulsion. That means, inter-electronic repulsion will also be there, and that is going to affect the electron cloud. Okay, previously electrons were only shielding the outer electrons, from the nucleus. Now the electrons are doing maramari on their own. So they are involved in themselves only. So the nucleus can pull out electrons. So electron clouds will expand. Clear? Because of interelectronic repulsion, size suddenly will increase. Okay. Understood? Clear? Repeating. Previously, the d electrons were only engaged in the shielding. Now they are also inter-electronic repulsion. So now inter-electronic repulsion plus shielding. Both are now shielding the outer electrons. So what will happen? The outer electrons can expand freely. Clear? Because this is getting more protection due to inter-electronic repulsion as well as due to the shielding effect of the electrons. So therefore, the electron cloud, they can expand easily. This is why near the end of each series there is a slight increase in the atomic radii. Clear? So what you are going to write in your answer, you understand? So in your answer you must mention that number of d electrons maximum at the end of a series, at the end of each series. This is one point. Next, inter-electronic repulsion. Inter-electronic repulsion predominate over nuclear pull. Predominate over nuclear charge and cause electron cloud to expand. Okay. So if electron cloud is expanding, size will increase. Did you understand? I am repeating once again. Near the end of each series, number of d electrons are maximum. So due to maximum d electrons, there is maximum repulsion. So therefore, the outer electrons, they are now getting protection from shielding as well as the inter-electronic repulsion of the d electrons. So now the nucleus cannot pull them easily. That is why they will be they will be expanding the electron cloud. Then so that is where the size will increase. So at the end of each series there is an increase in size. Next, third one. The atomic radii of transition elements. The atomic radii of transition elements increase on moving down the group. However, the atomic radii of elements of the second and the third transition series are almost the same. This is a very important part. First part is again easy. Second part might create a little bit confusion. Okay. The atomic radii of transition elements, we read out again. The atomic radii of transition elements increase on moving down the group. This is a simple question and the answer is due to increase in the number of shells. Right? Due to increase in the number of shells that we have already learned. So let us write it over here. Due to increase in number of shells. Already read in class 11. Second, atomic radii of the elements of second and third transition series are nearly the same. Mark it. This is a very important question. Very, very important question. The answer is one and only answer that you have to write. You have to mention this word in your answer. If you don't, you will not get marks. Answer is lanthanoid contraction. Lanthanoid contraction. Okay, this is seen from lanthanum. From lanthanum onwards, this is seen. This is why zirconium and hafnium, they cannot be separated. Why? Because 3D and 4D, because 4D and 5D series, they will have the same ones. So if they are having the same size or similar size, then how will you separate them? They are having the similar size, then their properties will also be similar. You cannot separate. That is why you cannot separate by using normal methods. Zirconium and hafnium compounds, Zn4 plus and Zr4 plus and Hf4 plus. Clear? So one and only answer that will be accepted is lanthanoid contraction. Due to lanthanoid contraction, there is a similarity in size of the second and the third transition series elements. Clear? Clear? Please mark this because it's a very important question. Next we have ionic radii. Ionic radii atomic radius for the atoms, ionic radius for the ions of that. So this is the basic part. It's written over here. Ionic radius decreases with increase in oxidation state. Very, very important. These are some theoretical parts which you basically have to remember. Decreases with increase in the oxidation state. So in case of periodic table, we have seen that as and when charge increases, ionic radius also decreases. In case of periodic table, we have seen charge increase, ionic radius decreased. Similarly, here also ionic radius decreases with increase in the oxidation state. Actually, the charge was only the oxidation state. That time you did not understand. But charge is only oxidation state, right? So if it is given different oxidation states and is asked to compare, then your answer has to be decreases with increase in oxidation state. Accordingly, you are going to mark your answer. If in the question you are seeing it is given same oxidation state, then you will go for nuclear charge. Nuclear charge more, then your radius will be less, and that is very obvious, right? Nuclear charge more means your radius cannot be more; it has to be less. So first thing you will see is if oxidation states are given different, যদি oxidation state যেগুলো দেওয়া থাকবে সেগুলো আলাদা হলে দেখবে যার oxidation state বেশি তার রেডি কম, যদি oxidation state সেম হয়ে যায় তাহলে যার নিউক্লিয়ার চার্জ বেশি তার রেডিয়াস কম। বুঝে গেছে? তাহলে রেডি ডিক্রিজেস উইথ ইনক্রিজ ইন নিউক্লিয়ার চার্জ ইন আ গিভেন সিরিজ, সেগুলো সব একটা সিরিজে চলে। বুঝে গেছে? তাহলে আয়নিক রেডি ইজ ভেরি সিম্পল। যদি নর্মালি দেখি অক্সিজেন স্টেট আলাদা দিয়েছে তাহলে ভেরি সিম্পল, যার অক্সিজেন স্টেট বেশি তার রেডি কম। ঠিক আছে, নেক্সট মেটালিক ক্যারেক্টার। মেটালিক ক্যারেক্টার মানেটা কি? মেটালে কি কি ক্যারেক্টার হয়? মেটালের ক্যারেক্টার হতে পারে মেটালস আর হার্ড, মেটালের ক্যারেক্টার হতে পারে মেটালস আর ম্যালিয়েবল, মেটালস আর ডাকটাইল, মেটালস আর হাই মেল্টিং পয়েন্ট বয়লিং পয়েন্ট, মেটালস ফ্রম আয়নিক কম্পাউন্ড, যেটা বেসিক ক্যারেক্টারিস্টিক্স, রাইট? লো আইপি এগুলো। নাও লেট আস সি metallic character of the transition elements. Transition elements metallic character কেন আর কিভাবে দেখা যায়? Transition elements show metallic character for two reasons. First of all, they have vacant d orbitals, because that is the definition of transition element. Transition element এর definition এই ছিল যে vacant d orbital থাকবে। তাহলে transition elements show metallic character because of presence of vacant d orbitals, আর second, low ionization energy. তাহলে এই দুটো কারণে মেটালিক বন্ডিং হয়ে যায়। না, হোয়াট ইজ মেটালিক বন্ডিং? মেটালিক বন্ডিং ইজ বেসিক্যালি, we just explain in one line or very simply let me explain. এটা হলো একটা এরকম বাক্স আছে, এর মধ্যে মেটালের not like this, sorry, diagram will also not erase. It's a big problem for me. See, every time I erase the diagram will come back. How many times I have to erase, I don't know. This is one circle, one metal, other metal, another ion, okay? These are all metal atoms. Here there is some center, okay? Nucleus, electrons are moving out, এখানেও electron আছে, এখানেও electron আছে। So all these electrons are moving in their outermost orbitals. So when the electron comes over here, this nucleus also exerts some force, okay? Similarly, this will also exert some force. Similarly, this adjacent will exert. Similarly, this will exert on someone. So this way, metallic bonding is formed within the particular metal. Understood what is metallic bonding? It is not a very separate type of bonding. It is this type of bonding is called metallic bonding. So more and more vacant d orbitals, if it is there, more and more type of the metallic bonding will be formed. And if there is low IP, then also metallic bonding will be favored. Clear? Because the outer electron can be knocked off easily, na? So it can be pulled towards by the other atom. Alright, so there are 2 points to note. First is low IP, presence of vacant d orbitals, and metallic bonding. Very important. Main point is metallic bonding. And why metallic bonding? Because of those two reasons. Clear? So if the question is asked transition elements show metallic character. Do not go for any nonsense writing in your answers. Simply your answer should be metallic bonding due to high metallic bonding. Okay, clear, due to high metallic bonding. And to avoid any sort of risk, write the reasons also. Why high metallic bonding? Due to presence of vacant d orbitals and low IP. Clear? Understood? Next. More number of unpaired electron. As you can see from the diagram, যত বেশি আনপেয়ার্ড ইলেকট্রন থাকবে তত বেশি টানবে বাকি নিউক্লিয়াসটা, তাহলে সেখানেও মেটালিক বন্ডিং বাড়বে। তাহলে যত আউটার মোস্ট ইলেকট্রন বাড়বে তত মেটালিক বন্ডিং বাড়বে। The second point is also saying that more number of unpaired electrons equal to more metallic bonding. তাহলে more metallic bonding মানে হলো more hard or more metallic character will be seen. Clear? This is also an important point. Please note it down. Next, this is why chromium, tungsten, molybdenum, same group, chromium group, are very hard, while zinc, mercury, cadmium are brittle. Obviously, zinc, cadmium, and mercury, they have zero unpaired electrons, so they will be brittle. That is why zinc is brittle compound, while chromium, tungsten, molybdenum, they have the maximum number of unpaired electrons, 6. Don't forget, it's not 5, it's 6. D and 1s also. Okay, so if the question is asked Cr, that is chromium, tungsten and molybdenum, or either one of the elements is given the question, it is asked, it is very hard. Why? Answer will be high metallic bonding due to maximum number of unpaired electrons. Did you understand? So according to the question you will be writing the answer. If the question is given as a general question that transition elements are showing metallic character, you will write this first part. If it is given chromium is very hard, then you will go for the second part, because chromium, at that time don't end up writing that presence of vacant orbital. No, because that in that case this particular specific point has to be mentioned, that there's maximum number of unpaired electrons. Clear? Understood? All right, next. This part I will delete, it's not needed. Okay, next we are moving on to ionization enthalpy. First of all, you tell me what is ionization enthalpy? The energy required to knock off an electron from the outermost shell, right, of an isolated neutral gaseous atom. That much definition you know. In periodic table we have learned about the IP of normal elements, representative elements, or whatever you go. But here in this case you're going to learn for the d block elements. So if you see the first point that is written over here, the ionization and energy or ionization enthalpy of d block elements lies between those of s block and p block elements, and they are quite high. So what do you think will be your answer for this? Though it's a very easy one, but what should be the answer for this? Yes. Very easy. Think properly, then you can answer. See, S block. S block is located where? On the extreme left of the periodic table. So if it is located on the extreme left of the periodic table, the nuclear charge will be lower. Right? Nuclear charge will be lower. As we are moving towards the right, nuclear charge increases. Right? And they are in the middle. So they have a higher nuclear charge as compared to S block elements. As compared to S block elements, first listen to me. As compared to S block elements, these guys will have higher nuclear charge. And as compared to S block elements, these personalities will have lower size, right? Lower size, smaller size, because size decreases from left to right. So transition elements, they are having smaller size, they are having smaller size and higher charge. IP will decrease. Apparently IP will increase, and it has to increase. Why? Tell me why? Because again, in periodic table you have learned IP increases across a period. So if I go across a period, IP will automatically increase. That also is a point to note. S block is on the left side, P block is on the right side, in between transition elements. So what will happen? Transition element is greater than S and less than P. Answer is very simple, that IP increases across a period. Clear? But we cannot write it directly in the answer. So what we will write is, we will write smaller size and high nuclear charge. Okay, smaller size and high nuclear charge. And second point you will write, though I will not tell you to write the second point, avoid the second point, avoid. Okay, avoid this point. IP increases across a period, because this is from 11. IP increases across period. Okay, from L to R. ठीक है? Understood? Clear? Simple part. Next one. The first ionization enthalpy. The first ionization enthalpy First ionization enthalpy increases with increase in atomic number across a given transition series, although the increase is not very regular. In case of transition or in case of wave block, we will not find a uniformity in most of the cases. Though in some cases we will find there is uniformity, but in maximum cases there will be no uniformity. So that will be very common for now. So that's not a big problem. But the problem is that first transition enthalpy is written increase in atomic number. See, the same point they are written in a different way. That's now I say IP increases across a period as from left to right, and that is your written increase in atomic number, because from left to right atomic number increases. Do you understand? It increases. So what will be the answer? Answer will be increase in nuclear charge. Simple. So your answer is going to be increase in nuclear charge. As we move from left to right, increase in nuclear charge. If atomic number increases, nuclear charge has to increase. Okay, next. The first ionization enthalpies of third transition series are higher than those of elements of first and second transition series. Yes, now tell. The first IP, the first IP of the third series is greater than that of those of the second and the first series. What could be the reason that suddenly the third IP, the third series, their IP went bigger? It's greater than those of the first two, while it should have been the first maximum, because down the group IP decreases, but that is not happening. Why it is not happening? My question is, why it is not happening? Yes. Think for some time, then I'm saying the answer. Okay, I think you all have thought. Let me now say the answer. Okay, let me say the answer. Okay, let me say the answer. Very simple. You tell me, if I follow the order, this is first transition, second transition, third transition. First transition, second transition, third transition. If I ignore transition, and if I say for basic representative elements, then it should have been that the third series very less IP than the first one, because number of shells increases, so nuclear pool will decrease. Correct. But that is also happening over here. Yes, correct. Number of shells are also increasing over here. I am agreeing to that. No problem. But what is the problem is shielding is not happening. What is not happening? Shielding is not happening. Why shielding is not happening? Because in the first and the second transition series there is no f orbitals. There is no f orbitals. But in the third series there is a f orbital also getting induced. Sorry, introduced. Right? So they have f orbitals, 4f orbitals. An f orbital is a very poor shielder, so it cannot shield. So if it cannot shield, then nucleus will pull the electron cloud towards it. So what will happen? You need more energy. Simple. Did you understand? So what is the main point of the answer? Main point of the answer is poor shielding effect of 4f electron. Poor shielding effect of 4f electrons. Clear? Did you understand? What question and what should be your answer? No beating around the bush, writing line, third contraction. I don't know where you people write something or the other. Next. This is a very important question. I don't expect it to come in the exam, but it is a good question. What is written as read? K2PCl6 actually is a complex. I have written like that format. I shouldn't have written it. It's actually a complex. K2PTCl6 should have been in a bracket. K2PTCl6 exists, but K2NiCl6 does not exist. But if you go to the periodic table and see, then nickel and platinum are in the same group. Nickel and platinum are in the same group. Then if platinum's compound can exist, then why not nickel's compound? But it does not happen. It does not. Nickel's compound does not exist. Did you get an answer? I think you did not. Alright, let us understand that. This is due to This is due to thermodynamic stability. This is due to thermodynamic stability of nickel ion and platinum ion. Both nickel 4 plus ion and platinum 4 plus ion. This is thermodynamic stability. If I assume this is due to thermodynamic stability. So let me explain what is thermodynamic stability. Thermodynamic stability is basically IE1 summation of IE1 summation of IE2 summation of IE3. Did you understand? This must be minimum. This must be minimum. If this value is minimum, if this value is minimum, then I can say that particular ion is stable. Compound of that particular ion is stable. So PT for PT4 plus this value is low, but for Ni4 plus this value is quite high. So Ni4 plus is not thermodynamically stable compound, sorry, ion, and its compound will also not be thermodynamically stable. That is why platinum's compounds are more thermodynamically stable and Ni4's compounds are not thermodynamically stable and they will not get them. Is it clear? Datas are there available, but datas will not be needed. What you have to know is this thing. Okay, PT4 plus is more stable than Ni4 plus, but PT2 plus is not stable, but Ni2 plus is more stable than PT2 plus. Okay, so these are some reasons that you need to know. So what you have to remember from here, what you have to write down in your answer. Answer is, let me write it. Simple answer, smaller the value of IE1 plus IE2 plus IE3, comma, greater is the thermodynamic stability of greater is the thermodynamic stability of that ion and its compounds. Did you understand? So IE1 plus IE2 plus IE3 এর sum করে যত কম ভ্যালু আসবে তত বেশি it will be stable. So for the same reason here Ni4 plus less than PT4. That is why PT4 compounds are thermodynamically more stable than Ni4 plus. ঠিক আছে? Okay, next. Oxidation state. Oxidation state is important part because এখান থেকে ছোট ছোট কোয়েশ্চেন তোলে। কিরকম পড়া যাক। Most of the transition elements exhibit several oxidation states because ট্রাডিশনাল এলিমেন্টস দেখো কি অ্যাক্টিনয়েড দেখো কি ল্যান্থানয়েড দেখো সবেতেই দেখবে ভ্যারাইটি অফ অক্সিডেশন স্টেটস এর অ্যাভেলেবল +2 +3 +4 +5 +6 all types. Why? Because of the energy gap between 4f sorry ns and n-1d. ns আর n-1d অরবিটালের মধ্যে যে এনার্জি গ্যাপটা আছে that is very less. So if the energy gap is very less, electronটা এখানে ঢুকবে এখানে ঢুকবে যেখানে ঢুকতে পারে। তো due to the change in the electrons, right, due to the change in the orbitals of the electrons can move from one orbital to the other easily. আর কতগুলো মুভ করবে, that is forming the oxidation states. Clear? So main point or the key point of the answer is the energy gap between these two electrons is very less. This one, the energy gap between the two electrons is very orbitals are very less. Energy gap between n-1d and ns orbitals are very less. That is why both these orbitals are available for bond formation. Clear? Clear? Next, this point is very important point. In this point, short question in MCQ format it can come, in fill in the blanks format it can come. Most common oxidation state in the first series is +2, but scandium cannot show +2. Except scandium, the most common one is +2. Next point. The bond formed in +2 and +3 state is predominantly ionic, while bond formed in the higher oxidation state is covalent. This is not a very important point, but remember it, okay? So bond formed in the +2 and +3 state are ionic in nature, while those formed in the higher oxidation states are predominantly covalent in nature. Okay? ठीक है. Next, within a group maximum oxidation state increases with atomic number. It's not an important point, just read. The highest oxidation state is +8. Very important, very important. +8 is the maximum oxidation state that can be shown by a compound, and if you see, it is shown by ruthenium and osmium. Both can show +8 oxidation state. That is, this is the highest oxidation state that can be shown by an element. Clear? Clear? Just check it out once. Next, formation of colored ions. This topic is somewhat associated with the next chapter, coordination compounds. So I will not discuss much about this. Right now I will speak only one word. Explanation of what is DD transition and what is DD transition, how it is happening, will be coming in the next chapter in coordination compounds. Okay. So formation of colored ions. Color will come from where? Wavelength. So that means some energy needs to be emitted, and when energy is emitted, according to Bohr model, energy can be emitted when there is a change of the electrons from one orbital to other orbital, right? Delta E is emitted. Delta E energy is emitted, which is equal to energy difference of the two orbitals. Correct? So that particular energy that is emitted, whatever wavelength that it has, if it is falling in our uh, visible region, then we can see that. If it is not falling, it will be falling under some other category, but it will be going. Clear? Point is that electrons are changing their orbitals. Now whether it can be the same orbital, it can be a different orbital. Because in case of d orbitals, they are degenerate orbitals when there is no ligand. But when there is a ligand, it is no more a degenerate orbital. It will split into two other orbitals. If I am saying, I will not discuss much because you cannot understand now what am I saying. In coordination, you will understand. For now, just remember that colored ions is due to DD transition. It is due to DD transition. That means electrons will go from one d orbital to other d orbital, because there is a energy gap between the two d orbitals, dx square minus y square and dxz are the two orbitals, and other three are the xz, yz and xy. This set of two orbitals, this set of orbitals will have an energy gap, delta naught. That energy gap will be giving the color. Clear? Okay. Now remaining part of this will be taught in the coordination compound. So you remember that colored ions are formed due to DD transition, and DD transition will happen only when there is electron free. Paired electrons will never do DD transition. So zinc, cadmium, mercury are colorless. Again same part, where they are having filled orbitals or they are not having any d electrons, then there will be no color. Clear? Next, magnetic properties. All sort of d orbitals, unpaired or paired. Unpaired hole paramagnetic, paired hole diamagnetic. Very simple. But the second point is very important, that maximum paramagnetism is seen in the middle of the series. Why? Again the same reason that came in the metallic bonding. In the middle of the series, maximum number of unpaired electrons are seen. If maximum number of unpaired electrons are seen in the middle of the series, then in the middle of the series only there will be the maximum paramagnetism. So chromium, molybdenum and tungsten will show the maximum paramagnetism. Clear? Okay. Next, catalytic property. You will find in most of the reaction, the d block elements and their compounds are acting as a catalyst. Reason? D orbitals are free. There is vacant, not free actually, vacant, because of vacant d orbitals. Second, variable valency is exhibited, or variable oxidation states are exhibited by the d block elements. And last is complex. But how complex formation is going to help us? Listen, reaction will proceed through that stage where activation energy requirement is lesser, right? So if I am going to form, if I can form some unstable intermediate, that is a complex, so the reaction will easily move because it is unstable. So it will require lesser activation energy, so I can go from that path to form my product. Clear? So if my catalyst can form complex which is an unstable complex, which is an unstable intermediate of that particular reaction, because we don't need that reaction, we don't need that product, that is an intermediate. So if it is forming an unstable intermediate, then the activation energy for that will be lesser because it is unstable. If it is stable, it will have a higher activation energy. If it is unstable, it will have lower activation energy. So that will require lesser activation energy. So I can go through that path. Clear? This is the reason why complex formation is necessary for catalytic properties. Okay, not only complex, any other unstable product if it is forming, it is going to act as a catalyst for that. Okay, next, complex formation. Why D block elements form complex? First reason is smaller size. Size of the D block elements is small. Second, nuclear charge is more. So size is also small and nuclear charge is also more. So it will easily attract. It will easily attract the ligands. The ligand that will come, ligand taki. Ligands are basically anionic molecules. It can be anionic, it can be cationic, it can be neutral molecules, which basically have at least one lone pair to donate to the central metal atom or to the metal atom. That is this D block element. Clear? And if they are going to donate the lone pair, then these guys must have some like body where they will accept the lone pair. So those bodies are vacant d orbitals. So there must be vacant d orbitals where the lone pairs will be accepted. Clear? Next, alloy formation. Alloy formation is basically again due to lanthanoid contraction. The sizes are almost same. Second series and third series sizes are almost same. So if their sizes are almost same, one metal can easily displace the other metals from their lattice to form a solid solution. If you remember in solution I told you that alloy is a solid solution. Alloy is not a liquid solution, it is a solid solution. Clear? So what is the point that you need to remember? That similar atomic size. Since they are having a similar atomic size, so one metal can easily displace another metal. Okay? This is very important. Complex formation, please read very carefully. Very important. Complex formation and catalytic property, both are very important. You can see directly 3 points are there in your paper. Simply write the 3 points. Whichever the teacher has in the marking scheme, they will give you marks on that. Clear? And if you cannot remember, at least you will write the major point. That is d orbitals. Both the case, d orbitals are empty. And you have to write. The remaining 2 points after that you write. Okay. This ends our D block elements, not completely. The theory part of D block elements ends here. After this, we have reactions of D block elements. That is your potassium permanganate and your dichromate. Okay, that we are going to deal with the next class. Now we are going to the inner transition elements. So transition element বুঝতে পেরেছো? Transition element এর মধ্যে লুকিয়ে থাকা কয়েকজনকে আমরা periodic table বাইরে বার করে দিয়েছি। Those are the inner transition elements. Periodic table এর শেপটা distort হয়ে যাওয়ার জন্য we have shifted them out of the periodic table. Clear? So those two separate rows will be called as D block elements. D block elements. Not D block, it is F block elements. Okay. So under F block elements, we will read about two things. That is called lanthanoids and that is called actinoids. Lanthanoids are those people who are following lanthanum. So there are basically two types of people. One is following lanthanum, one is following actinium. So those guys following lanthanum will be called as lanthanoids. Those guys following actinium. So those guys following actinium will be called as actinoids. Clear? First F block series or first F series is lanthanoids, second F series is actinoids. Filling of 4f electrons take place in lanthanoid and filling of 5f orbitals take place in the actinoids. Lanthanoids start from cerium 58 and end at lutetium 71, while actinoids start from thorium and end at lawrencium. Okay. 90 to 103. So total under lanthanum and actinium there are 14 elements, not 15 elements, because lanthanum and actinium is not a part of the F block elements. Major people make mistake over here. It's 14 elements in this, not 15. Okay. Okay. Let us see the next. Electronic configuration of F block elements. See, F block elements is actually a very complex topic to read. Complex topic to read in the sense is, first of all, some people of, not some people, actinoids to entire series is radioactive. And in case of lanthanoids, you have one guy, prometium. Other than that, all are non-radioactive. Correct? So, other than that also, size is very huge. So, it is difficult to actually study. So, what theoretically we have got? Theoretically, we have found out that the configuration of this will be Xe xenon 4f to the power n 5d1 6s2. This is a theoretical. But if we see practically, then this will not be the same. It will vary. Why? Because the 4f orbitals and the 5d orbitals, they are having almost similar energy. The energy gap is very less. So if energy gap between 4f and 5d is very less, electron is going into which orbital, that only I cannot identify. So there is an anomaly over there. Okay. Next, general characteristics. The characteristic which we have learned for D block and F block as well. General characteristics of oxidation state. First point. Common oxidation state of lanthanoid is +3. Both lanthanoid and actinoid have +3 oxidation state. Maximum oxidation state of lanthanoid is +4, while for actinoid it is +7. These are the small points which will be asked in the fill in the blanks, which will be asked in the MCQs. Okay, so general characteristics under that first point is oxidation state. The common oxidation state of lanthanoids and actinoids is +3. Clear? Next point. Number 2, magnetic properties. Both actinoids and lanthanoids show paramagnetic nature. Simple. Show paramagnetic nature due to presence of unpaired electrons. Next. See, these are all done. It's easy. Next. Next we have color of ions. For D block elements, the color of ion was due to, for D block elements, the color of ion was due to DD transition. For this it is FF transition. Clear? However, this phenomenon is somewhat difficult. It is difficult as F orbitals are more important. F orbitals এর বাইরেও তো আছে না, 4f, then 5s is also there. So however, this phenomenon, that is this FF transition, is actually very difficult. Why? Because first reason is F is very inside. That's okay. F is inside and they are well shielded by the previous electrons. So F orbitals being very inside and being well shielded, there will be lot of anomalies. That is why FF transition is not actually seen. Clear? But if you are going to get a question why there is actinoids are colored, or why lanthanoids are colored, or why the F block elements are colored, then answer will be FF transition. Don't write DD transition because then this don't happen over here. Next, very important, ionic and atomic rating. First, let us understand lanthanoid contraction. See here, if I talk about lanthanoid contraction, what happens is basically, then I am explaining this. moving from left to right, size decreases. We know. Achha. So if I start moving from cerium to lutetium, we are moving from left to right. So nuclear charge starts increasing to increase in atomic size. So nuclear charge increases. That is a very obvious one. No problem is there. Chalo, theek hai. As we are moving, the added electrons enter in F orbital, 4f orbital, right? So they are entering into the 4f orbital. Chalo, ढुकचे. Shielding effect of 4f orbital is very improper, বা very poor. প্রথমত f অরবিটালের শেপটা দেখেছো 7 degenerate orbital, very অদ্ভুত একটা শেপ হবে, what shape god knows what shape, but some very অদ্ভুত type of shape. So due to that, the poor shielding effect. So if shielding effect is very bad, then what will happen? The charge that is experienced by this f electrons will be more, right? It will be more. So this causes a slight reduction in size, because f orbitaler বাইরে যে ইলেকট্রন গুলো আছে সেগুলোকে ঝাঁক করে টান মারছে না নিউক্লিয়াসটা, because f orbitals are poor shielders. So if f orbitals cannot shield the outer electrons, the electron cloud is getting pulled in every time. More and more f orbitals are coming inside. Clear? So size keeps on decreasing, like very slowly it keeps on decreasing. Okay. So electrons are getting added. Increase in effective nuclear charge, steady contraction, পরপর contraction হচ্ছে. Total effect of entire thing will be called as lanthanoid contraction. Clear? বুঝলে? Similar thing also happens in actinoid. In case of actinoid, the term is just actinoid contraction, but the thing is same. What is same? Understood? Left to right, we are moving. Basic concept, left to right, nuclear charge increases. Aki concept, nuclear charge increases, size decreases due to poor shielding of f electrons. As we move ahead, the size keeps on decreasing steadily due to addition of more and more f electrons. The total effect on all the lanthanoids are called lanthanoid contraction, and total effect on the actinoids are called actinoid contraction. Simple. Clear? So what is the point? That as we move as we move from left to right, there is a steady decrease, or there is a uniform decrease, or there is a regular decrease in the size of lanthanoid and actinoid due to lanthanoid contraction and due to actinoid contraction. Clear? So what you have to focus over here is regular decrease in the size, decrease regularly. Okay, decrease regularly, because it's a regular decrease for both ions and metal atoms. Now very important question is here. Lanthanum hydroxide is most basic, while lutetium hydroxide is least basic. Why? Lanthanum is starting. Lanthanum is the starting of lanthanoid series. It is not a part of lanthanoid series, but starting. And ending is done by the lutetium. But so why? What has happened that lanthanoid is more basic and lutetium is basic? For this, you have to go back to class 11. What you have learnt in class 11? Fajan rule. So Fajan rule says what? Fajan rule says if cation size is lesser and anion size is bigger, then covalent character increases. And covalent hydroxides are acidic. Simple reason. So you have to write your answer like this. According to Fajan rule, cation size decreases, then covalent character increases, so basic nature decreases. Clear? So that is why lanthanum 2 plus lanthanum 3 plus size is very huge, so covalent character is lesser, that is basic. But lutetium size is smaller because it is on the extreme right, so that is why covalent character is more, so basic character is less. Did you understand? It's very simple logic, and this is done in class 11. Fajan rule has been done in class 11. Okay, next. Complex formation. Lanthanoids can form complex, but it does not, due to f orbitals are very deep. Clear? But it can form complex. I don't think that it cannot. It can form complex which are chelating ligands. Chelating ligands. That we read when we read again coordination. We will read about chelating ligands. It can form a chelet. Chelet means like a ring type of thing, like this. Ring type of thing. It does not look like this. There is a central metal atom like this. Like this type of thing. A ring will be formed. This will call a chelet. We'll read that. Not now, but we'll read it in coordination compounds. So this lanthanoids, they can form complex with the chelating ligands, but actinoids, they have a greater tendency and they can form with pi complex only. Yes, sir, pi complex only. Sorry, they can form with pi bonding ligands only. Directly, they can, for the normal ligands that are available, they will form with pi bonding ligands only. But lanthanoids, they will form with chelating ligands. That will lead to the next stop. Okay, next. Formation of alloys. They will form alloys because they are high density. They have high density and melting point is also high. Simple things that are not there. Last topic of today, lanthanoid and actinoids the comparison that will be asked in the exam. Maximum oxidation state for lanthanoids is +4. For actinoids it is +7. Lanthanoids show paramagnetism, but it can be explained very easily. Actinoids also show paramagnetism, but it cannot be explained very easily. Then lanthanoids are non-radioactive other than prometium, while actinoids all are radioactive. Clear? Lanthanoids do not form complex easily, but form with chelating ligands. And for actinoids, they have a greater tendency to form complex, and they can form it with the pi donating ligands only, or pi bonding ligands. Okay. Last is the uses of lanthanoids. You can see there are so many uses given. 6 uses are given from your book. This is just copy and paste because I have nothing to explain. Now, what is written? Let's just read it once. What is written? Mish metals. Mish metals is basically alloy. Mish metals contain 30 to 35% of CDM along with smaller quantities of this is written. Check. Magnesium alloys containing are used for making parts of jet engine. Pyrophoric alloy again is a type of alloy containing rare earth metals that is in preparation of ignition device. Cerium salts is contained analysis. Dye. Cerium phosphate catalyst, and this is neodymium oxide, prometium oxide, coloring glass, and optical filters. Thorium and compound is in nuclear chemistry. Uranium is used in atomic reactors. Thorium oxide is used in incandescent glass mantles. Thorium salts is electric cancer. Uranium salts is in glass industry. Clear? So that is all that you need to read from D and F block theory part. In the next lecture, the second lecture, I will take up the reaction part. Okay. So I hope that you have understood today's lecture. Please read the chapter because there's a lot of things to remember actually. There's a lot of reasons. So those reasons only you have to remember. Once you remember the reasons properly, you will find that inorganic chemistry is actually easy. In physical chemistry, you have to do numericals. In organic chemistry, you have to understand. There you cannot memorize everything. But here you can memorize and get marks. The problem is, you will not do that. And then you will say, we cannot do inorganic, but that's not the case. Read, you will get it. Okay. So thank you. We'll meet very soon.